Okay, thanks a lot for the reminder. Yeah, it's my first time to do a workshop in the collaboratory, so I hope you can give me some advice if I think, yeah, I didn't say something clearly, and if you have any questions, you can also interrupt me anytime. So first of all, I like to give a brief introduction to myself. So I'm currently a postdoc in the Department of Statistics, and I get my PhD in statistics in 2021, and also from UCLA. Here is my email, and I think you can also see this email on the website of Collaboratory. So if you have any questions regarding this course, or if you have any questions regarding statistics, yeah, in the future, when you do your own research or have some problems, you can always come to me for advice. My research interest is mainly about developing statistical methods for genomic and biomedical research, with a focus on false discovery control in feature screening. I'm also interested in risk model in disease prediction and statistical rigor in biological analysis. So this is the first time I teach this course, so I'm not 100% sure whether the topic I cover is something that all of you are quite interested in. So during this course, if you find that you have something that you are specific interested in, you can tell me. You can send emails saying that, oh, for example, you want me to introduce one topic. I can consider adding those topics into the lectures tomorrow and the day after tomorrow. And from my current plan for this first day of the workshop, I will introduce linear regression, including simple linear regression, and reveal p-values and hypothesis testing. I want to introduce these because I think it is the most basic concept of statistics, and I think it is important to know, have an accurate understanding of this concept so that you can make good inference of p-value results in the future. Okay, I see a question. This is about from Eloy. And I like to introduce how to diagnose whether the linear regression model is a good model for your real data. And finally, I'd like to introduce something about multiple linear regression. This is my current plan, and I'm not sure whether I can cover all these topics today. And if I cannot, I will put some of the contents into tomorrow. I understand that in the previous workshop, there is an introductory workshop about statistics, and in that workshop, we also have some knowledge about linear regression. But here I would still like to introduce linear regression because I think it is very basic and important. And after introducing the simple linear regression, I think it's easier to expand this concept to some more complicated regression models, including the models that I like to introduce in the following days, including the logistic regression, Poisson and negative binomial regression, Cox regression. I will introduce these models in the second day, and I would like to also introduce Lasso, which is one analyzed linear regression model. And on third day of the workshop, I would like to introduce something about multiple testing, because when we do regression models in many biological data analysis, for example, GWAS and feature screening, we will do regression models multiple times. And it is important to correct the p-values from multiple regression models using multiple testing techniques. So I would also like to introduce how to do multiple testing. And when we use regression models, sometimes the model may be so correct, so there will be some problems about model misspecification. So I would like to show what if the model is incorrect, and how this model misspecification may lead to questionable biological conclusions. So, and finally, I'd like to give my suggestion of how to generate a negative control dataset to validate whether the model you are using is correct or not. So this is the current plan for my workshops. So if you want me to cover any topics that may be related to regression in the following days, you can just tell me and I will consider adding those. I will mainly use the software R for my workshop because this is the most popular software for statistical analysis, and it's free, and you can download this from this link. I have already sent an email about installing R and R Studio, and I hope all of you have already have R and R Studio installed. So I just want to make sure that have all of you installed R and R Studio. If any of you haven't, you can let me know, and maybe I can give you some minutes to install that, because I will use this software a lot in the following workshops, and I will give you some practice during this workshop so that you can play with R with the provided data sets yourself. So I think it's better if you already have R and R Studio installed. So, okay, so then I like to introduce why I like to introduce regression. So the regression models want to model a functional relationship between a predictor variable and a response variable. Here, the predictor variable is the input, and it can be independent variable, covariate. And we want to use these predictor variables to predict the response variable, which is the output. And there are many examples for regression models, and I like to introduce some of the examples in the following slide. And maybe you can think about what example you can think about, which can be solved using regression. Yeah, I think if you have been doing some research or class projects regarding biological analysis or statistical analysis, I think we will have some experience or some idea on how we can use regression models. We want to use regression models because the real world is noisy. We can not always use a formula, such an equation, to describe the relationship between one variable and another variable. We have noise, and this noise may come from observation noise or process noise. So here, observation noise means that, for example, when we want to know, for example, what's the for in biological analysis, a very common amount is the number of reads in a region, in a genomic region, for example, the reads in a gene or the reads in a lung region. So when we count the number of reads, we may have observation noise because this number, we cannot always capture all the reads from the experiment. So this noise can be the observation noise. And another noise comes from the process noise. For example, when the relationship between one variable and another variable is not fixed. For example, we know that when for a child, when the age becomes larger, the height may also become larger. But in some case, the child may, for example, have some disease, so it grows slower. So in this case, the relationship between one variable and another variable is broken, and such broken relationship may attribute to the process noise. So the noise may come from different sources, and these noise make it impossible to use an equation to describe the relationship. So we want some models that can have a brief understanding of a relationship, and it also allows the existence of the noise. And there are two distinct goals for regression models. The first is to understand the relationship between predictor variables and response variables. So as we have just discussed, so we can see, so if we use the regression models to describe the age and height of a child, we can know that, oh, when the child becomes older, it will also become higher. Another thing is to do prediction, and this is more like using for future response, predicting the future response given a new observed predictors. For example, when we already know that the trend of the height of the child from 1 year old to 10 years old, and maybe we can do some predictions what the height will be when the child is 11 years old, which is not observed so far. I'd like to introduce some, okay, this is about the history of regression, why we have the word regression. So it actually is from Sir Francis Galton in 19th century. He studied the relationship between height of parents and children and noticed that the height of the children will regress to the population mean. And this how this word regress comes from. So regression starts as the term to describe statistical relationship between variables. And here I'd like to introduce some examples. So for example, in epidemiology, we can use regression models to relate lifespan to obesity or smoking habits. In science and engineering, we can rate physical inputs to physical outputs in complex systems. And in education and income, we can relate the income to the length of education. So there are a lot of applications of regression models. And here I'd like to introduce one more example, which is, I think, which is very important analysis in high throughput biological analysis, which is called the identification of differentially expressed genes. I will introduce this example in all these 3 days of lecture because I think it's one of the most important and basic analysis of high throughput biological data analysis. So in this analysis, we will have the measured read counts for different genes from samples of different conditions. Here we have 2 conditions, and these 2 conditions can be one cell type versus another cell type, or cancer versus normal samples. So in summary, we will have 2 conditions. And within each conditions, we will have several samples. Here, each row is the sample and each column is a gene. So we have 3 samples from each of the 2 conditions. And we want to identify genes that have different expression values from the 2 conditions. So one way to solve this differentially expressed gene analysis is to use regression models. And it is used by several very popular bioinformatics tools. And they will use the condition as the predictor and use the counts as the response to see whether we can predict counts using the conditions. If we can predict, it means that the condition have an important role in the expression levels of the genes. And if not, it's not an interesting gene. So we can see that for this gene, the counts in condition 1 is much smaller than the counts in condition 2. So if we use a regression model to describe this relationship, we'll see that the condition is an important predictor, and this gene is an DE gene. And for this gene, we can see that the expression values between the 2 conditions are quite similar. So if we use a regression model, we will see that the condition is not an important predictor, and we will say that this gene is not a DE gene. So it is an important application of regression models in biological data analysis. oh, and like, okay, I like to introduce the aim of the course. So what I expect I can teach for this course. So I like to I would like to make sure that you can predict the response from the predictors using regression models. And you will know that what kind of model should you use given the dataset, and which variables should you include, and which transformations of variables and interaction terms should you use. And given a model and some data, and you will know that how can you fit the model using the data, and how can you make inference of the model parameters. And finally, how do you regularize the model to avoid overfitting and other related issues. So let's start from the simple linear regression. Yeah, I think it has been already introduced in the previous workshop, but here I like to emphasize the mathematical formula of this model, which was made in the previous workshop. So this is the mathematical formula of the simple linear regression. So if we use yi to denote the response variable for sample I, and use xi to denote the predictor variable for sample I, then the model is yi equals to beta 0 plus beta 1 times xi plus epsilon I. So here epsilon I is an arrow random variable. So as we have just introduced, we can never use an equation without a noise to describe the relationship between two variables, because we always have noise in real data. And in linear regression models, we make the arrow term part of the model, so and which is epsilon I here. The distribution of this arrow random variable is not specified. And here we can start to look at why we need linear regression by looking at this example dataset. So I have already sent this dataset to you through the email yesterday. So I think you already download this dataset. So maybe you can just start from some basic R techniques. So first, maybe we can use R to load this dataset. And then we can use a scatter plot to show the relationship between arm span and height, and to see whether we can see there is a close relationship between these two variables, and whether you think linear regression model is a good fit to describe this data set. So maybe you can go to your R Studio and start from this dataset to generate a scatter plot. And if you have finished, you can let me know. And I will also do this on my side. So I will. So if you have finished, you can type in your chat box to let me know that you have finished. And if all of you have finished, I will go to the next part. So I will also do this myself. So if you are not quite sure about how to do this, you can just follow what I have been doing. or if you have any questions regarding reading the dataset into R or other issues, you can just let me know. So here I read this dataset into R using this read.csv command and function, and this will be the location of the file, and I put this file in this directory, and your file will be in different directory from your laptop. So you just need to make sure that this is the location of the file and the location is correct, so that you can read this file into R. And here I'm using R Markdowns, and it's also okay if you are just using the R script, and these two are the same in terms of their commands. Okay, I see Amelia raise your hand. Okay, it seems that you have finished.
Yes. Hi, thank you. Just quickly, how do you determine how, like, where to look for your, or where to find the directory that you're loading in? I know I've saved the data set into a specific folder, but how to know the syntax?
Okay, so here, for example, if I so for example, if I search the name of the data set, and I will know that. So for example, I can, if I'm using Mac, I'm not sure whether you're also using a Mac. So if I search this in English, and I can find that the location of this data set, and if I go to the get info, it will give us the detailed location of this file, and you can copy this location to R, and this will also be a location that you can use in R. Yeah, that's
Perfect. Thank you.
That's either way to get the location.
Okay, but without doing that copy, you had put the quotes, tilde, backslash, and then starting your directory name.
Yes.
Okay, thank you.
Oh, no problem. Oh, it seems that I cannot use this. It's a little different. Yeah, change this into slash. Oh, I understand what happened. Let me change this. Okay, this should be good. Okay. Yeah, I see some of you have finished. Maybe we can just wait for 1 more minute. Okay, so have everyone finished, or is anyone still working on this?
Do we need any specific packages for this workshop? Should I install anything specific?
I don't think so. For today's workshop, no, but we may need some packages for tomorrow. Okay, so maybe I can continue. So we will get a scatter plot, something like this. So we can see that there is very clear trend that with a larger arm span, we have a larger height, which is also same as our intuition. So it seems that the dots in this figure can be looked as a round line from this left bottom corner to upper right corner, and we will have an impression in our mind that here we should have a line and all the dots are round line. So, and this is the perfect case for the simple linear regression, that the dots can be considered around a line. And yeah, this is our regression model, and I think I have already introduced this. And here, one more thing that you like to say that is that so here, if the dots can be seen around the line, and we can always use beta 0 plus beta 1 xi to represent the line in the 2D space, and the epsilon I will be the arrow, because not all the dots are exactly on that line, so they are apart from the line. So the difference from the dot and the line will be this epsilon. So in this linear regression model, we assume that this epsilon is a random arrow 10 with mean 0 and variance equal to sigma square. And we also assume that the random arrows from different samples are independent. So these are the two important assumptions for linear regression models. So if you don't remember what expectation is and what variance is, here I will also have some slides about expectation and variance, and I will not go to those two slides today, but I will send those slides to Eloy, and he will upload these slides onto the website so that you can refer to those pages if you are not so familiar with what's the expectation and what's variance. So from this part, we can see that the response yi have two components, beta 0 plus beta 1 times xi, which is a constant term because there is nothing random about this part. So if the model is perfect and we don't have random terms, it means that all the dots are exactly on the line, but this can never be the truth for real data analysis. And the difference from an ideal case to a real case is this random term epsilon I. So this describes the difference between the dots and the line. However, as we expect that the epsilon, the random term, has a mean 0, which means that the average or the expected value for yi is the expectation of these things, which is the expectation of a constant and the expectation of the random variable with mean 0. So we can see that the expected value for the i's observation is exactly on the regression line. So it means that for each dot from the regression model, we expect that dot to be on the line, but it's not on the line because we have some random errors. And for another dot, if we know the x values, we can predict the y values or the response values of that dot by using this constant value, because this is the expected value of that new observation. So this is just a review of the expectation. You can go to these if you are not so familiar, but it's totally okay if you don't know these mathematical things, because I will not introduce anything mathematical today. And okay, so we can see that from the previous equation about expectation, we can see that the response yi comes from a probability distribution with mean equals to beta 0 plus beta 1 times xi, which is the regression line values. And okay, so this means that the regression function is this. So it means that for each x, so this is for the i's observation, and for each x, we can always use this to describe the relationship between y and x. Okay, so it means that the regression always talks about the average of, or the mean of the probability distribution of y for a given x. We can never accurately describe the relationship y and x, but we can describe the relationship between the expectation of y and x. So all the relationship are between the mean and given the x. Okay. Okay, this is something more about the error terms. So the response yi in the i's trial exceeds or falls short of the value of the regression function. So it means that the dot can be larger or smaller than the expected regression line, and the difference will be the error term epsilon I. So if the epsilon I has a larger variance, it means that the dots can be far away from the regression line, and if the variance is small, it means that the dots are close to the regression line. So the variance describe how well the dot is close to the regression line. Okay, so as the beta 0 and beta 1 xi, these amounts are all fixed and constant, the variance of yi only depends on the variance of epsilon I, because it is only thing that is random. And as we have already assumed the variance of epsilon I is sigma squared, so we can see that the variance of yi is also sigma squared. So it means that the variance of the dots depends on the variance of the random errors. Okay, so this is introduction to the variance, and I will skip this, and you can refer to these pages if you are interested in these. Okay, so now we can start our first regression model. Here we have the arm span dataset. If we want to predict the height using the arm span, we can make the arm span as our predictor X and the height as our response. Then how can we predict a person's height using the person's arm span? So it means that how can we use the X and to predict Y in our previous scatter plot? So it means that we want to find a line that makes all the yi's are close to the lines as close as possible. We want to find a line, and that line can be represented by b0 plus b1 times xi. Sorry, b0 plus b1 times x, and for each observation I, then we want yi to be close to b0 plus b1 times xi. So, and we want to make this distance as small as possible. So if the line is close to each dot, then it is a good line. And if the line is far away from some of the dots, then that line is not a very good line. So for example, let me just make some examples in this figure. So in this figure, there are multiple ways to generate a line. For example, we can lines h equals to 68. this is one way to get generate. Okay, so it oh, sorry, my bad, AB line. So here this function AB line can be used to generate add a line to the plot. So here H means horizontal. Here I just add a horizontal line with this y-axis equals to 68. So this is such a line, and we can also have another line to describe to this figure, and I will do this. Okay, AB line, A equals to 0 and B equals to 1. So it will be another line. So here the AB line, A equals to 0 and B equals to 1 means that we add a line y equals to x to the plot. A is intercept and B is slope of the AB line function. So we can clearly see that this line is better compared to this horizontal line, because if we look at the horizontal line, some of the dots are far away from this line. For example, this dot is far away from this horizontal line. So it is not a good fit. But if we compare the horizontal line with this diagonal line, which has intercept equal to 0 and slope equals to 1, we can see that many dots are exactly on this line and most dots are quite close to the line. So we have an impression that this line is better compared to this line. But how can we accurately describe the closeness of the dots to the regression line? We want to use a formula, mathematical formula, to describe the closeness. And we want to find a line that have the smallest distance between the dots and the line, so that this line is good enough. So here I'd like to introduce how we use mathematical formulas to describe how different dots are close to this line. A very simple idea is to minimize the distance. For example, for each dot I, the distance between yi and the regression line is yi minus b0 plus b1 times xi. So this is the distance, and we can minimize this distance for each dot line, and we can sum the distance from all the dots to make it represent the distance of all the dots. However, remember that this distance can be either positive or negative. So if it is above the line, it is positive, and it is below the line, it is negative. So you should consider this thing that if it has a large positive value or a small negative value, they are both bad. So we need to add something to replace the distance into some positive measurement that can also represent the distance. So here one proposal is to minimize the absolute value of the distance. However, this proposal is hard to solve because here we have absolute values, and absolute value is something that is hard to deal with in optimization. So finally, we have our final proposal, which is the square of the distance. So here, after we take the square, this distance is always positive because the square of anything is positive. So we want to make sure that the measurement of the distance is always positive for each of the observations, and we sum up all these distances. And we use Q to describe this amount, and we want to minimize Q by finding the B0 and B1, which can make the whole thing the smallest. So it is how we solve the simple linear regression model, and this is called least square estimator. So here least square means that we want to find the parameters which can give us the least squared distance, or means least squared errors, which is a term used in statistics. So this is error, and this is squared error, and this is sum of the squared error, and we want to get the least sum squared error. So to solve this optimization problem, we may use some calculations, and we might, if you are interested in this, you can find this solid solution online. And here I would like to briefly introduce how we solve this. We can take the derivative of the whole formula and find the B0 and B1, which can make the derivative equal to 0. And that B0 and B1 will give us some optimal values of the whole sum squared error term, and then we will get the best B0 and B1, which can minimize the whole thing. So this is how we solve the regression models. And I would like to introduce this because this is the most important statistical part of regression models. For different regression models, the difference between them are just in this formula. Different regression models will have different chance to be minimized, and some will have some penalty or some modification to this, but they will also all have similar formats. And the goal of all regression models is to minimize such a term to describe the distance. So if you understand this, this will help you understand all other regression models theoretically. So do you have any questions regarding this least squared linear regression?
What part were you pointing to when you were saying that all other regressional models just change this part?
Yeah, I will say that the Q part, this formula, this is the core part for all regression models.
As in the structure is the core part for all regression models.
Yes, different regression models will have different formula for this. Aside from convenience, are there any other benefit to using square distance instead of absolute value distance? I will say that the main, I'll say that the main advantage is just the convenience, because it is, we cannot using, for example, taking derivative to solve the absolute value formula, but we can using the squared. And I think the convenience is the main reason for using the squared term. And thank you for your question. Okay, and now I will introduce some results, some toy examples about the intuitions behind the least square regression. So the first is a horizontal line. So this horizontal line is, so if you use the horizontal line as the regression model, you will see that it can still minimize the first proposal. If you just take the y-axis of this horizontal line, the y values equal to the average of all the y's, then you will have that the sum of the errors equals to 0. But you can see that it is not a good regression line. So the first proposal is not a good one. And this proposal is a good one because it minimizes the squared error, and every dot are quite close to this line. Okay, this is how we solve the minimization problem. And here I just gave a brief introduction. I think you can solve this yourself if you are interested in this. So you can expand this this sum squared arrow, and you take the derivatives and you set both equal to 0, and you can solve these two equations and get the B1 and B0. And this will be the results, because I will not do the algebra here. And this is the results after lot of algebra. And we will get the B1 and the B0. And you don't need to remember what B1 and B0 is if you just want to use regression as a tool for your analysis. But I think it's interesting to know how all these things come from. And now after all this, we can do our regression ourselves. So let's go back to this data set. And in R, we can use a function called LM. The LM function is a function to do linear regression. And we can use this function in this way. So we can use LM. We will first have the variable that we want to make as the response, and then it follows another variable which we set as the predictor, and finally we should let it know that what data set we are using. So we are using the arm span data set. You can also name the data set as another name. In that case, you should change this part, and you can use this function to do the linear regression, and you will know what are the estimate coefficients. So here, if you just run this command, you run a linear model predicting height using arm span, using the dataset arm span, you will get the coefficients. So here the intercept is the B0, and arm span coefficient is B1. So this function will help you do all the algebra and give you the predicted B1 and B0s. So maybe you can also repeat this on your side. Okay, so if you have finished, I will also show the results of this linear regression. So I will first generate a plot, scatter plot, and I will also add the regression line to the scatter plot using the API function with the intercept and slope estimated from the regression model. And this will be the results. And we can also compare this regression model with the previous regression model, where we use y equals to x as the regression line. We can see that this line is better compared to y equals to x, because you can see that for these two dots, you can see that they are quite far away from the y equals to x. but they are quite close to this new regression line, which is based from the linear model. And you can, so from this comparison, you can see that this regression model is better, and actually it is a line that minimizes the sum squared error. Okay, so far we have introduced how we solve the optimization problem, how to solve the least squared minimization, and I would also like to introduce some assumptions regarding the error tens. We can see that no matter how the error tens epsilon I are distributed, the least square method provide unbiased estimators of beta 0 and beta 1. However, in many cases, we not only need the value of beta 0 and beta 1. In many cases, the thing that we are interested in is whether these two things are indeed related. It means that we want to infer whether beta 1 is large enough or whether beta 1 is not equal to 0. So these questions are inference of the coefficients. And to make such inferences, we need to specify the distribution of the error tens. For example, if we want to calculate somewhat the p-value for these regression models, so that we can make some inference regarding the coefficients. In this case, we will need the assumptions regarding the distribution of the epsilons. In most cases, when we assume that the epsilon are normally distributed, and this will be the updated model after we adding the normal assumptions for the epsilon I. So the first what we have just introduced. So yi are the response, beta 0 and beta 1 are parameters, xi are the known predictors. And here, finally, we assume that epsilon I are identically and independently distributed. And they all follow a normal distribution with mean 0 and variance sigma square. So note that the assumption for epsilon I only for inference of the result. So if you only want to find a beta line, you don't need this results, but if you want to get a p-value, you will always need this assumption. And in many cases, this assumption can be violated. And it is why it is very important to do diagnosis analysis after the regression analysis. And I will introduce that part later. So first, maybe we can have some time for practice and rest. So in the following 10 minutes, maybe you can play with the dataset, the CAS 04 dataset. And first, you can use a scatter plot to show the relationship between horsepower and the suggested retail price. These two are two columns of that dataset. You can use similar function that I have introduced about to generate such a scatter plot. And then you can use linear regression to fit this relationship, and you will get the coefficients. So what will be the intercept and what will be the slope. And you can play with this data set and take a risk as you finish it. And I will give you 10 minutes for this. And let me know if you have any questions and problems. record. So is anyone of you would like to share your results to others?
Sure. Just sharing what the coefficients are.
I can let you share your
Or
screen.
share screen. Sure. Don't mind my notes that I put in.
Yeah.
Oh, it says
Yeah.
it will stop sharing your screen.
Yeah. I stopped.
So I'm over here and we loaded the data set and then we plotted horsepower and suggested retail price. And then we added the LM function to fit the model, and then added AB line to plot the regression line on top of the model. So this is the output for LM. And then this is the plot with the regression line, the best fitting model for this. And stop me if I am, if you're seeing anything.
Yeah, I think that's very, very good.
And then I had a question here of just like, because I'm used to using the pipe operator and I just haven't loaded the packages. But so it's just, if you put AB line, will it just map onto the last plot in the code?
Oh, sorry. I just have found one problem about your code set. So
Yeah.
literally from my slides, I'm asking to predict the sorry, I didn't make it clear. Oh, I think they didn't make any mistakes. Sorry, that's my bad. So because from my previous from my initial thinking, I would say that I would like to predict suggest retail price using horsepower. So I would make suggest retail price as response and horsepower as predict. But I think it's fine because I didn't make it clear. So that's my problem.
My bad. I can just switch them. But okay, cool. Thank you.
Okay, so
can we say that can we say that this is not a good model, or because I guess, like, what can we conclude from our linear model? Because the dots look kind of far away from the line. Can we say anything?
So maybe do the line first. I haven't finished myself. So I think, so first, it's very good question. Yeah, you made a very good point that you think that the dots are not so close to this line, and you think that maybe not. For example, this dot is quite far away from this, and this dot, so these dots are not so close to the fitted regression line. Yeah, that's very good point. And that's why it's very important to always important to check whether the regression model is good enough. And we have a lot of ways to check it, and I will introduce how to diagnose later. Yeah, and you made a very good point that, yeah, it's true that from our intuition, this plot is not as good as the previous one. And that's why I think we may need to do some modifications later. Yeah, very, very good point. Oh, okay. I also see, yeah, Jennifer made a good point that if you use summary, you can see the R square and the significant level of the coefficient, and that will tell you some information about if the model assumptions are right, whether we can have enough evidence to reject the null hypothesis that beta 1 equal to 0, such inferences. Yeah, that's will also help you interpret the model. But there is also a very important thing to know is that we may need to diagnose the model before the inference. Yeah, you two both make very good points. And yeah, thanks for your questions. Sorry. Okay, I will go back to my slides. And okay, so as Jennifer has said, we may need to do inference regarding the coefficient. For example, after the regression, we know that what beta 0 is and what beta 1 is. And the value itself is not so informative because from the value itself, we don't know whether this slope is large enough, because even from some random values, we may still have a large beta, but that may just come from random. So we want to know that whether the slope is larger than the effect of randomness. And this is something which is related to hypothesis testing. And hypothesis testing is one of the most important part of statistics. So I will have a review of hypothesis testing in the following slides, but here I would like to put the problem out first. So here we will have a null hypothesis, which is the hypothesis that we think we can make any mathematical conclusions from. So for example, here we assume that what if the coefficient is equal to 0? So this will be our null hypothesis. And we also have the alternative hypothesis, which is that the beta 1 is not equal to 0. So these two are opposite to each other, and we want to use our data to tell us whether any of these two hypotheses is true or not. So the use of null hypothesis is for helping us having some conclusions or having some inference about the data set. And I will use the example later to show how it works. And if the null hypothesis is true, it means that the slope is 0. And so if we come back to our previous figure, and this one will be a null hypothesis, because it means that the height has nothing to do with arm span, so that the base, so we don't have any linear relationship between these two variables. So all the difference between the heights of different people are totally from randomness. And in this case, the slope is equal to 0. And we call this a null hypothesis. So as we know that it is just a hypothesis, so it can be false. So for example, we do see a clear relationship, and in that case, we will reject the null hypothesis. So in that case, we say that the null hypothesis is not true. We reject that one. And now I would like to do some review of the hypothesis testing. There are 4 elements of a statistical test. First is null hypothesis. Second is alternative hypothesis. And then we have test statistic, and we have rejected region. I will introduce these 4 parts one by one. So I understand that many of you have already know these things from a course and or something somewhere else, but I would always highlight these elements of statistical test because we always use a lot of p-values in our research or in our projects, or a lot of things will have p-values. But I think it's important to know how these p-values come from and what p-values are about. And in that case, we will not give some p-values that doesn't make sense, because there are indeed a lot of p-values that are from problematic tests or violated assumptions and bad hypothesis testing problems. And knowing these basic elements will help you avoid those problems. So first, let's come to the null hypothesis. Sorry, here is an extra slide about what are the errors about the the hypothesis testing. So when the hypothesis is true, sorry, now when the null hypothesis is true and we reject the hypothesis, we call this type 1 error. And when the hypothesis, when the alternative hypothesis is true and we did not reject the hypothesis, we call this type 2 error. These two terms are about the errors regarding the hypothesis testing results. Oh, okay, so this is now hypothesis of the regression model. So this is the one figure of the regression model. So we can see that if the null hypothesis is true, then B1 will be around 0. And we can see that when we have some dots, we can fit a regression line, and that regression line will be different from this null hypothesis. And we will say that the further this regression line is from 0, the less likely that the null hypothesis is to hold. So this is the intuition for why we need null hypothesis. We first have a null hypothesis, and we use evidence to reject this null hypothesis so that we can say we don't believe the null hypothesis, so that we can make conclusions that the beta 1 is not equal to 0 when our evidence is strong enough. And this gives us another intuition why the null hypothesis is always something equals to something. So this we always have an equal sign in the null hypothesis. It is because that when the null hypothesis is true, we want to compare the data from the null hypothesis. So the null hypothesis should be something that is fixed, so that we can compare something else with that fixed thing. And if the null hypothesis is not fixed, we cannot know what it is, so we cannot make comparisons. So that's why the null hypothesis is always something equals to something. And here we are interested in whether the slope is not equal to 0, or whether there is linear relationship. So it is why it is the null hypothesis whether beta 1 equals to 0. Okay, and this is alternative hypothesis. If the slope is not equal to 0, you have to determine whether that deviation would be surprising given the model and the sampling distribution of the estimator. If it is sufficiently different, we reject the null hypothesis. Okay, so we have the null hypothesis, and then we also have the alternative hypothesis. And then we want to have a test statistic that have some distributions that is known when the null hypothesis is true, so that we can get some inference whether that test statistic is too small or too large or normal. Okay, so in statistics, data are all finite sizes, and different finite sets of samples produce different point estimates of beta 0 and beta 1 given the same estimation procedure. For example, for the arm span and height regression model, we can sample, for example, people from this district, or people from UCLA, or people from USC, or people from a company. Different sample will give us different results. Although it is possible that the relationship between the height and arm span is the same for all these samples, but the randomness in the samples will give us different estimates of beta 0 and beta 1. So for example, the beta 1 and beta 0 estimate from students in UCLA may be different from the beta 0 and beta 1 estimate from USC. These betas can be very similar, but they are still likely to be slightly different. And this will be the randomness the randomness for these estimates. So the key point is that the estimated B0 and B1 these two coefficients are random variables, and the randomness comes from random sampling. So these two coefficients will have some distributions. And if we know the distributions of these two random variables when the null hypothesis is true, we can make some inference. And what are the distributions of these estimated coefficients? So here is how we construct the test statistic in simple linear regression. So we know that these two things are random, and we want to know the distribution of a test statistic of these coefficients. So okay, so we know that B1 is an estimate for beta 1, and it is from some calculation we will know that this B1 is normally distributed with mean equals to beta 1, and we will also see that B1 minus beta 1 over sigma over the variance of B1 follows a normal distribution with mean 0 and variance equal to 1. So this is there is something that we know the distribution. And we also need to, however, one problem here is that we cannot know the exact true variance of the coefficient B1. So we also need to estimate this thing. So if we use S2 squared to denote the estimated variance for the coefficients, and we will have this formula that B1 minus beta 1 over SB1 follows the T distribution when the null hypothesis is true. So okay, and this will be the test statistics for linear regression. So with the null hypothesis true, we know that this thing comes from a T distribution, and we know that when the T distribution when a value comes from very large or very small value, and it is likely to be from a T distribution. And in this case, we will know that when we get a very large test statistic or very small test statistic, it is not likely to come from this null distribution, and it is something against the null hypothesis, and it is how we do hypothesis testing. Okay, so, and this will be the summary of the test concerning beta 1. So the null hypothesis is beta 1 equals to 0, and the alternative is beta 1 not equal to 0. And the test statistics T star will be beta, so it will be B1 minus 0 over SB1. So as SB1 follows very complicated formula, I will not introduce it here, but yeah, most softwares will help you calculate the T statistic from the linear regression, but I think it's important to know how these come from. So we can see that all these tests are based on the assumptions. One key assumption is that the normal is that the random errors follows a normal distribution, and the random errors are independent. This may be the case. They may not be the case for real data, and that's why some p-values may be problematic. Okay. And okay, this is the test, and we can get a p-value from the test. This is about how we get the p-values. We have an estimate of the sampling distribution B1 from the data, and if the null hypothesis holds, the B1 estimate coming from the data should be close to 0 in this case. But we need to put this consideration into formality. P-value is the probability of obtaining test result at least as extreme as the result actually observed. So in this case, the p-value is a probability that we observe a value which is more extreme, or at least as extreme as the t statistic calculated from the data under the assumption that null hypothesis is correct. So it will be a probability that the t, a random variable from this t distribution is smaller than t star. So I forgot to add the absolute value here. And if we still use this t star as the estimated t statistic, we will reject the null hypothesis if the p-value calculated is greater than the predefined threshold alpha. Here, we use alpha equals to 0.05 in most cases, and we may have different thresholds for different analysis tasks. So here, alpha is just a predefined threshold, so which describes how confident we need about the results. If we have a small alpha, it means that we need to be more confident about the results. Okay, so let's go back to the COS04 dataset and arm-span dataset and calculate the p-values of B1 from linear regression. And I will also introduce something I think may be very important to help you understand the properties of p-values. I will use some simulations to show how p-values work. And I will generate some random covariate and predict this random covariate using horsepower, and I will see what the p-values will be like. Okay, let's do the first part. So let's do the linear regression and calculate the p-values. So I think Jennifer has already mentioned it. So if we already do the regression models, for example, we look at the COS04 dataset, and we use horsepower to predict the jet retail price. We can use a function called summary to get the p-values. If we use, if we define the results of this linear regression as model, and we can do summary of the model to get the p-values. And you can repeat this on your side and let me know if you have finished. So the only thing we need to do is to define the to use a variable to define the results of the linear model, and then we make it as the input of the summary function. And the summary function will output all the inference results for the regression model. Please let me know if you have finished. Okay. Yes, thank you. Okay, I see most of you have finished, and let's go to the results of the summary function. So we can see that in the results, we have a coefficient part. And in this part, we can see the t statistic and the p-value for the intercept and horsepower, which is a predictor. Here we are interested in the t and the p-values for the horsepower. And we can see that the t statistic is quite large and the p-value is very small, and it is smaller than 2 times 10 to the negative 16. So it is very, very small value. So we have enough evidence to reject the null that the coefficient equal to 0. So we can make a conclusion that horsepower is indeed related to the suggested retail price, and it can be used to make the prediction. And that's how we make conclusions. And another thing I like to show is how we can is about how to use simulation analysis to help understand the properties of p-values. So here I like to do some simulation analysis, and I will still use the class 04 dataset. So I will just copy most of the code here. And what I will do is that I will add a random variable, which comes from a random distribution. They are just from a normal distribution and random values. So they are nothing to do with the suggested retail price. And I can use the R-known function to do this. So R-known function can help you generate random variables from normal distribution. For example, I say R-known 10, it will generate 10 random variables from normal distribution with mean equals to 0 and variance equals to 1. So here I want to generate as many random variables as the observations of the class 04 dataset. So here I generate a large number of random variables from normal distributions. So we can see that we have more than 200 random variables, and they are totally random. And then I will use these random variables to do the regression models. So in this case, this random variable is not related to the suggested retail price, because the random variables are just, this random variable is just from random. So it has nothing to do with the suggested retail price. So this is to illustrate what if the null hypothesis is true. So in this case, the null hypothesis is true, and we can see what will happen. So first, maybe we can still make a scatter plot to show what the data looks like, and we can do a summary. What does the n-row function do? Okay, the n-row function calculates the number of rows for this data set. So for the class 04 dataset, we have 234 rows and 13 columns. So if we count the number of rows, it will be 234. So and I want to generate as many observations as the class 04, and that's why I use the n-row here. Okay, let's do the analysis again. So we can see that if we look at the scatter plot, we can see that the suggested retail price seems to be uniformly distributed along X, and which shows that this random variable is nothing to do with just retail price. And if we do the p-value calculation, we can see that the p-value is quite large. So that it means that. So you could also, okay, I see. So you could also use n colon. Actually, it is not n colon, but n col. So you want to calculate the number of colons, you can use this function n col to calculate. And if, for example, if I use this, you will have 16 as the number of columns for this data set. Okay, no problem. So this is an illustration about what if the null hypothesis is true. So in this case, the random variable has nothing to do with the response. So we can see that if we still want to do linear regression and fit the model, we can see that the p-value is large. And if we set the significant level equals to 0.05, then this p-value is greater than the threshold, so that we will not reject the null hypothesis, which means that we believe that these two random variables are not the same. But pay attention that even the p-value is very large, you can see that the estimate slope is still quite large. So it means that, oh, sorry, my bad. That's not the coefficient. Let me see where the coefficient is. So okay, let me just look at the coefficient. So you can see, okay, I didn't, it's no problem. So you can still see that the coefficient is still very large. So if we want to make a plot, you can see the slope is still quite large. So this gives us intuition that when we see a slope with very large absolute value, it does not mean that this relationship is significant. We only need to pay attention to the p-values instead of the slope, the value of the slope. A large slope doesn't mean that we do have the relationship, and that's something that need to be kept in mind. And this is from one simulation. And I also have a question, so I might have just said in this slide. So if we generate a random covariate and predict this random covariate using horsepower, okay, that doesn't matter. Yeah, what will the p-values be like? It will be large. And what else? So how do you expect the distribution of the p-values to be? So what will be the p-value distribution of p-values like? This is the question. What is the distribution of p-values if the null hypothesis is true? So does anyone has any ideas or guess? So how do you expect the distribution of p-values be if the null hypothesis is true? Does anyone has any ideas? Okay, no problem. I will introduce what the distribution of p-values will be. So from this example, we can see that when the null hypothesis is true, p-values will be large. It is our intuition because in this case, we do not want to reject null. And here I have to show what the distribution of p-values would be like. So first, from this simulation, we will get one p-value, and we can repeat this simulation multiple times to get multiple p-values, and then we can look at the distribution. And I will do it now. So we can use a for loop for this. Okay, I will first define a vector. P-values equals to Oh, sorry. Okay. So here I use the rep function to generate a repetition of 1,000 zeros. So if you look at the p-values, it will be 1,000 zeros. I just use this as an empty vector to store all the values for 1,000 simulations. And then I have a for loop for I in 1 to 1,000. I will repeat this simulation. Okay, so for each of the random simulation, I first generate a random variable, and then we do the linear regression, and then we model summary equals to summary model. Okay, then we get the summary of the model. So I will let you know what the summary of the model looks like. So if we look at the model summary, it's just the thing that we have seen. We will get the p-values for each of the covariates, and then we will extract the p-values from this list. So we will get the coefficients of this, and this will be the coefficient, the table of the p-values and the t-values standard error of the covariates. I just use these to get the p-values. Okay, it will be the second row and the fourth column. So all these are just to extract the p-values from the summary of a linear regression model. Okay, so for the i's repetition, we will first generate a random variable and then use this random variable to do a linear regression, and then we will look at the p-values from that linear regression. Okay, and then I will get 1,000 p-values, and I will look at the histogram of the p-values. Okay, and let's do this. It may take some time. Okay, you have the histogram of the p-values. Okay, so we can see that the p-values are uniformly distributed when the null hypothesis is true. So you can see that we have a uniform distribution from 0 to 1, which is a range of the p-values. This is a very important property to be keep in mind about p-values. Which is p-values, always follow a uniform distribution when the null hypothesis is true. So, and this is also an important technique to be used when you want to check whether you are using the correct model. For example, when you already know that the null hypothesis is true and you calculate the p-values, you can, if the distribution of the p-values is not uniform, it means that the calculation of p-values is problematic. A reasonable p-value always follows a uniform distribution when the null hypothesis is true. And you can use this to check whether your model is correct. So if the model is incorrect, the p-values may be too conservative or too small. Both may be possible, and in both cases, the p-values will not be uniformly distributed, and this will be an indicator that the model is incorrect. And I think it is something that is very helpful to check the model. Does anyone has any questions? Okay, for this is
Yeah,
for
sorry,
okay,
sorry,
go ahead.
I have, so sorry. I just have a quick question, and maybe I kind of missed it while you were explaining it. The last line, the 50th line, which says p-values in square brackets I model dot summary, what does that line do?
Oh, this line. So this is just to get the use this object to store the output of the summary model, because we want to extract the p-values from the output of the summary function. So I think it's more convenient to first use this object to store its output, and then use to go to the specific entry of this output to extract the p-values. This is just for convenience.
Okay, got it. Okay, thank you.
Yeah, no problem. Okay, and that's for the properties of p-values being the null hypothesis true. And let's go back to our slides. Yeah, I think the results for the class 04 datasets has been shown. And if you are interested, you can do the arm span part as part of your homework. I don't think I will have any other homework other than the practice from these slides, but you can make the parts that haven't been done during lecture as your homework. And yeah, if you want me to check whether you are doing things correctly, you can send your result to me, and I will tell you whether you are doing things correct. But I will not have any other homework. Okay, let's go to our next slide. Okay, and this is about what if the regression model is not good. And this is called remedial measures. This is about how do we know that the regression functions is a good explainer of the observed data. There are two ways. The first is to make some plots, and second is to make some hypothesis testings. And when the regression model is not a good explainer, what can we do? One way is to transform the variables. And I think this is a case that we have talked about the class 04 dataset. We may use horsepower to predict suggested retail price. We can see that some those are far away from the regression line, and it seems that the assumptions are likely to be violated. What can we do? Yeah, this is very important for linear regression models. And for doing this, there is a concept which is very important, which is residuals. Let's have a review of the predicted response value, which is yi hat equals to b0 plus b1 times xi, where b0 and b1 are the estimated coefficients and xi is the predictor value. And we can see that the estimated value may be different from the actual response value. And the difference between these two values is called residuals, which is defined as yi minus yi hat. And we need to note that this residual is different from the random error, because the random error is a random variable, which is unknown, but the residual is something that we do know. This is the difference between these two things. In a normal regression model, the epsilon i's are assumed to be independently and identically distributed from a normal distribution with mean 0 and variance equal to sigma squared. In this case, if this assumption is true, we would expect that the observed residuals EIs, which are estimates of the errors, should also reflect these properties, so that the residuals should also identically distributed and follow the normal distribution, and also they should be independent. And that's why we can use residuals to check the assumptions of the linear regression models, because the most important assumption is about the random errors, and this, which is the IID normal assumption. So it is the assumption that needed to be checked. And should be started by residuals. Okay. We will know that whether the regression function is linear and whether the error tails do have constant variance and whether the error tails are independent. And we can also check whether we have some outliers and how these outliers may affect the results. We also check whether the errors are normally distributed. We can check all these by looking at the residuals. And there are some plots that can be used for checking these things. And first is the plot of residuals against the fitted values. And we also have plots of absolute values or squared residuals against fitted values. We also have normal probability plot of residuals and plot of residue against average. I will introduce all these plots later and one by one. Okay, this is a brief practice, and we can first use R to generate the residual plots for height versus arm span, and look at the, for this practice, we can first focus on the height versus arm span comparison, and we can generate the residual plots by using this function, plot model, where model is the output of the linear regression. And we can have a first brief look at of the results, and we will discuss the results later. And okay, as we have already had, okay, it's already 6:30, so we may have 10 more minutes rest. So we will use these 10 minutes to generate this plot and also for the rest. And I will show you how to generate these plots first. So first, we go to the linear regression model, and this is model predicting the height using arm span and using the data arm span. And then we can plot this model. And okay, and then we will have 4 plots. You can try this on your own laptop, and you can try to interpret these plots from your intuition. And we also have 10 minutes rest. And this is the code, and you can do it yourself, and you can think about how to interpret these plots, and yeah, we will have the rest. Okay, let's come back to the lecture. And I think everyone has already finished the diagnostic plots. And yeah, I will introduce these plots one by one and show how we can use these plots to help us to decide whether the model is good or not. So the first kind of plot is the first one, the plot which shows the relationship between the residuals and the fitted values. So the x-axis will be the fitted values. So what will be the y hat, and the y-axis will be the residuals. So here we have 4 different types of the residual plots, A, B, C, D, and yeah. So from your intuition, what will be a good residual plot? You can type your answer in the chat box. Okay, thank you for your answers. Yes, the answer should be A. And yes, this plot shows whether the residuals are identically distributed. So for example, for B and C and D, we can see that there will be a trend in the relationship between fit values and residuals. So this shows that when for different observations, their distributions of residuals may be different. For example, for this case, the larger the predictor is, the larger the residual is. And the larger the residual for a larger risk predictor, that distribution will be different from the distribution of the residual from a small predictor. So in this case, the residuals are not from the same distribution and the assumptions is violated. So we will expect to see that the residuals of all the observations come from the same distribution. So we go back to this plot, we can see that although there will be some up and side downs, but overall we will see that all the residuals are in a similar scale and we do not see a clear trend. So this red line is a fitted line of the trend of the residuals, and we can see that it is quite smooth and we do not see a very clear trend. And this is the first plot. And we go to the second plot. This plot will be the plot to check the normality of the error tens, and it is called the QQ plot. The QQ plot is to check whether a list of random variables comes from a specific distribution. And this QQ plot will see whether these residuals comes from a normal distribution. So it will plot the numeric quantiles on the horizontal axis and the actual quantiles on the y-axis. Here are some examples of non-normality in distribution of error tens. So we can see that if the QQ plot, a good QQ plot should have all the dots on the diagonal, and the bad QQ plot can have the dots either skewed right or skewed left or symmetrically with heavy tails. And if we go back to this plot, we can see that this is the x-axis is the theoretical quantile. The x-axis is the theoretical quantile, the y-axis is the residuals, and we can see that the residuals has exactly the same distribution as the theoretical quantile of the normal distribution. So we can see that the normal assumption is not violated here. So this is for the second plot. And for the third and last plot, we will look at the actually the third plot is called the scale location plot, and different from the first plot. The first one is called the residuals, and the third one is standard square root of the standard residuals. So it shows the so here all the square root of standard residuals are positive, and we will see that whether there is a trend here to say whether I think this is for the same purpose as the first one, but it is more focused on the scale of the residuals to see whether the scale has a trend. And as if the assumption is not violated, we do not expect to see any trend. But if there is indeed a trend, it means that the residuals are not from the same distribution. And for the final plot, we will look at outliers and the data points which has large influence on the results of the linear regression. So here we come to a concept called leverage. So if we go back to the last plot of the last diagnostic plot, which is called residuals versus leverage. So we can see that the y-axis is standard residuals and the x-axis is called leverage. And we also have some lines which are about the Cook's distance. I will introduce these terms one by one. And the first one is called leverage. The leverage will describe whether a dot has large impact on the results of the linear regression. If a data point has very large leverage, it means that if we change the value of that data set, the results will also be changed a lot. So these data points will be some data points that we need to pay attention to. And another measurement is called Cook's distance. And Cook's distance will measure the effect of removing a point. If a data set has very large Cook's distance, it means that if we remove that data point from the data set, the results of the regression will be changed a lot. So here we can see that all data points don't have small Cook's distance and small leverage. So we do not have large outliers. You may you may not have an impression what a large leverage or Cook's distance is, and I will show you what it is in the following example. And I will use the cost data set as an example, and I will also answer the question proposed before about whether this is a good linear regression model. First, this is the regression model which predicts suggest retail price using horsepower. And then we can use plot function to generate the diagnostic plot. Let's see what the 4 panels look like. The first plot is the residual versus fit value plot. So from this plot, yeah, we can see that it's true that some of the residuals have much larger values compared to the other. For example, these 3 values seems to be outliers. The residuals are very, very large. And we also see that it seems that there is an overall decreasing trend in the residuals. And yeah, this trend indicates that the residuals are not from the same distribution. Overall, this plot is not so bad because the trend is not so clear. But if we look at the QQ plot, which look at whether the residuals come from a normal distribution, we'll see that many of the residuals are far away from the diagonal, which means that the distribution of the residuals is far away from a normal distribution. The actual quantile is different from the theoretical quantile. So if we see such a shape, it means that the normal distribution assumption is violated. And let's look at the next plot, which is called the scale location plot. So this plot shows the relationship between this square root standardized residuals and fitted values. and to see whether there is the location of the point will affect the scale of the residuals. And we can still see that now we can see a very clear trend, a very clear increasing trend for this plot, which means that with the larger fitted values, we will have larger standardized residuals, which further validates that the residuals from different data points do not follow the same distribution. With larger fitted values, the residuals are likely to be larger. So all these plots shows that the assumptions needed are violated, and the linear regression models may not be the best one for this case. And let's look at our last diagnostic plot. So here we can see that if we look at the leverage, you can see this point, data point 223 has very large leverage. And it also has very large standardized residuals. A large leverage means that by changing the y values of this data point, the results of the regression will be changed a lot. And the larger standard residue also means that this data point seems to be an outlier. So these two things together shows that if we remove this data point, the regression results will be changed a lot. And this is also represented by this high Cook distance. You can see that this data point has a Cook distance greater than 1, which shows that the whole regression results is driven by this single data points, which is likely to be an outlier. So all these results indicate that the current regression model is not perfect, and we may need to do some improvement. Maybe we can show, okay, I see Amelia has some questions.
I'm having a little bit of trouble understanding how to read this plot in terms of, so the y-axis is the standardized residuals, but how are we determining the Cook's distance for a given data point? I'm not really following that.
Okay, so I will introduce this figure again. So this figure is about the residual versus leverage.
Right.
Yeah, if a data point has a very large residue, it means that this data point is far away from the regression line. And this data point is likely to be an outlier. So this is first information. And second information is leverage. The leverage shows how important this data point is. And it shows the potential effect of this data point. If a data point has high leverage, it means that if we change the value of that data point, the regression with the results will be changed a lot. And Cook's distance can be considered as a combination of these two. So if a data point has both has high leverage and high standardized residue, it will have high Cook's distance. Like this data point, it has its Cook's distance is greater than 1. So we can consider all the data points below this line have Cook's distance more than 0.5, and data point between these two lines has Cook's distance between 0.5 and 1, and data points with Cook's distance above 1 can be considered data points which are very influential in this data set, and they can be both outliers and effective points. And if we remove this data point from the whole data set, the results of the regression will be changed a lot. And maybe I can use the result to see whether how the results will be changed if we remove this data set. So first, we can run a first model using the first data point, and then we can have another model using the same data set, but removing the 223 observation, and we can see what's the difference. So we can see that, okay, maybe in contrast, I can add another model which randomly removed, for example, the first observation. So in this case, we will have 3 different models. This first model is the original model. The second model is a model after removing the most influential data point. And this one is a model which from removing a not so important data point. So we can see that if we compare this model with this model, we can see that the slope has changed a lot, has dramatically changed. So it decreased by about 12. But if we compare this model with this model, we can see that after we remove the first data point, the results are not change a lot. But if we remove this very important data point, the results will be dramatically change. So it means that we may have to pay much attention to this data point to confirm whether it is an outlier, whether we need to remove a data point, because the existence of this data point will change the regression models a lot. And this data point can be identified by looking at the diagnostic plot. And that's why we need to do such diagnosis after the linear regression.
Thank you so much. That makes a lot of sense. And so I think that, so anytime that you're creating these summary plots, the sort of Cook's distance dotted line will be plotted onto this, and you can kind of see which, if there's any data points that are at a large Cook's distance.
Yes.
Okay, thank you.
Yeah. Okay, no problem. Thank you for your question. Okay, so far we have seen what a good diagnostic plot like and what a bad diagnostic plot will be like. And now I would like to introduce how we can solve the problem of a bad linear regression. And it is how to fix. If simple regression model is not appropriate, there are 2 choices. First is to abandon the simple regression model and develop and use a more appropriate model. For example, the logistic regression model will be introduced in tomorrow's course. And there is also a way that may be simpler, which is to use some transformation of the data so that the simple regression model is appropriate for the transform data. And I will use introduce this way to fix the model today. And I will introduce this method called Box-Cox transforms. This is about we can make some transformations of the response. We can do some transformation of the response. For example, in our previous example, we are predicting suggest retail price using horsepower, and we can see that the result does not seem very good. But what if we do not predict suggest retail price? What if we predict log of suggest retail price, or square root of suggest retail price, or square of suggest retail price? In this, the regression model may be better after doing such transformations, and the Box-Cox transform will help us to design the best way to do the transformation on the response. There are also some methods to be used to make transformations on predictors, and you can, if you're interested, you can also search for those methods. Okay, and let's see how they will do the transformations. Here are some examples. So actually, they will do some power transformations on the responses. And you can see that if they will out the Box-Cox transform will include different power transformations. If we including a parameter called lambda, this lambda is a power for this transformation. So if lambda equals to 2, it means that we make response to be the square of the original response. If lambda equals to 0.5, it means that we make the response square root of the response. And they further define that if lambda equal to 0, then we do a log transformation on the original response. And we will also do, for example, the inverse and inverse of the square root such transformations. So we can do different kinds of transformation of the y's, and then we can see whether the results will be changed after doing such a transformation. And I think this technique is very important in many biological data analysis, because in many cases we are interested in, for example, log counts or log of the variable of interest to make the model have a better performance. And we can do this, we can do this by using a function called Box-Cox. And sorry, I forgot about this, but we may need to install some packages for this function. And this package, I think, is a very basic package called MASS. And this package is very helpful for some basic regression models and statistical analysis. And if you have not installed these packages before, you can use this command line to install this package. You can use install.packages, and you can type the name of the packages here, and then you run this command, and then you can install the package. After installation, you can use the library function to use this package. And I will first library this package and run the Box-Cox function to help us decide what's the best transformation on the response. So let me still use model to denote the linear model for this price horsepower analysis. And we can use the function called Box-Cox. On the original, on the model output to get the result. Okay, so you can, if you have not installed this package before, you can try this command to install it. And after you successfully install this, you can run this code to see what the results look like. And also, please let me know if you have finished. Okay, has everyone finished? Or if you have any problems about installation, you can also let me know.
So I just want to, so we want to transform the data in order to have it be better predicted by a linear model. Is that correct?
Yes, that's correct.
But how is, I guess I missed the definition of transformation, but how is changing the scale of the data going to change how a model fits it? Because it's the same data, it's just at a different scale.
Oh, okay. So for example, if you can consider, so for example, if the, okay, if we go back to this trend. So this is the trend of the fitted values against the residuals from the cost data set. And we can see that with the larger value, the residuals also have, the residuals also larger. But if we, for example, if we do a square root of log transformation for the data set, then it is possible that the trend becomes flat. And we still see that the different data points have the same scale of the residuals. And it is possible that the difference in if the only thing that contribute to the difference in the residuals are from the scale of the data, we can use transformation to make the data set have data points have similar scales, and then it will reduce the difference. And then the model assumptions may not be violated in this case, and the linear model will be a good fit here.
Okay.
Okay, so I guess, yeah, you have finished this part, and yeah, let's try to interpret the results. So here we can see that we can see a curve as the output of the Box-Cox function, and it will tell us what will be the best choice of lambda if we want to do transformation. So from this plot, it seems that the lambda equals to 0 seems to be the best among all the lambdas. And yeah, and in that case, we can, if we go back to the definition of the Box-Cox transformations, we will see that lambda equals to 0 means that we can do a log transformation on the response variable. And let's do this and to see whether the results will be changed. So we can just follow the result of the Box-Cox, and then we do a linear regression model, and we change the response from suggest retail price into log of suggest retail price. And let's see what the results would be. So if we look at the QQ plot, we can see that compared to our previous QQ plot, it seems that now all the dots are much closer to the diagonal, which shows that the data points are likely to be normally distributed. The residuals are likely to be normally distributed. And if we go look at the residual versus fitted value plot, we can see that it seems that the residuals are quite close to be the trend much closer to be flat, although we do see some up and down trend, but if we look at the majority of the data points, we can see that they are uniformly distributed around the 0. And if we go back to the scale location plot, you can also see that the standard residuals seem to be in the same scale for different fitted values. And we compare to our previous plot, we can see a much better trend for all these three plots. And if we look at the final one, we can see that. So this time, this data point don't have a large, it still have large leverage, but as its standardized residuals has much smaller scale, its cook distance is smaller than 0.5. So the results of this regression is much more stable after the transformation. All these diagnosis plots shows that after we do the transformation, the new model is a much better model compared to the original one, which means that maybe it's better to predict the log of suggested retail price using horsepower instead of the original suggested retail price. And we can see how data transformation will affect the linear model and how it will make the violated assumptions not violated anymore. So does anyone has questions regarding this part? Okay, if not, I will go to our final part. Okay, I see a question. In this example, how would you explain why it makes sense to do a log transformation of the price? Intuitively, what does it mean to take a log of the price, and why does it give us better results? Yes, it's a very good question. So if I will explain the results from this view. For example, if the horsepower has a linear trend of suggested retail price, so let's look at the scatter plot first, and I think it will be good to look at a scatter plot, and I think you made a very good point. How do we interpret the results of the regression transformation? So first, let's look at the scatter plot, which suggests retail price versus horsepower D. Okay, let's first look at the scatter plot and consider the shape of the log transformation. So we can see that if we do not do log transformation, the trend of the relationship between price and horsepower seems to be in this shape. It seems that when the horsepower increase and when the horsepower is already very large, the increase in horsepower will lead to larger price increase compared to an increased horsepower in a small range. My intuition is that when we buy cheap cars, for the cheap cars, the increase in horsepower is not so important compared to the increase in horsepower for expensive cars. I think it makes sense to me because it is more expensive to increase horsepower from, for example, 300 to 310, 330, or compared to increasing the horsepower from 100 to 150, because when you already reach such a large horsepower, you are already buying very expensive cars. And when you buy very expensive cars, the price has much larger scale increase when you choose different brands or different types, and the effect of horsepower will be much larger for those expensive cars compared to cheaper cars. And we can also see this trend I plotting the results. For first, we can generate the AB line as we have done before. Let me see the coefficients of the AB line. Okay, it's here. Okay, so this will be the linear regression line, and I can also generate the regression line again using the using the fitted value from this. Okay, model. Okay, I will make x-axis as the horsepower and y-axis, which is the predictors, and the y-axis will be the fitted value. And after we take the potential. Oh, I forgot to order those data points. Okay, so you can see that the black line will be the linear regression line, and the green line will be the regression line after we do the data transformation. And yeah, from our intuition, we can see that seems that the green line fits the overall trend better compared to the black line, which is also our results from the Box-Cox transformation. Okay, I hope this answer your question. And does anyone else have any questions? Okay, thank you. Okay, and let's go back to our final part, which will be the multiple linear regression. I guess I may not have the time to finish all of the parts, but then no problem, we can continue tomorrow. The first is the multiple regression. The multiple regression is one of the most widely used tools in statistical analysis. And the matrix expressions for multiple regression are the same as for the simple linear regression. And we can also write the similar mathematical formulas. First is why we need multiple predictors. It is because that if we only use one predictor, it may not explain everything of the response. So we may need multiple predictors for better prediction results. For example, if for the spam filtering, we may use different properties of an email to decide whether this email is spam, because a spam message may have different, take different forms, and we may use different properties to decide. And we also can use different factors to predict the revenue of the company. And first, I would like to introduce the most simplest case first order with 2 predictor variables. So here we, different from our previous simple linear regression, here we have 2 different predictors. For each observation I, we have xi1 and xi2, which are the 2 predictors for the i's observation. And it is called first order because we only consider the first order terms of these 2 predictors. And we may also have, for example, second order terms in a more complicated regression model. An important thing is how to interpret the regression coefficients. For example, in this model, other than beta 0, which is the intercept, we have 2 coefficients, beta 1 and beta 2, for these 2 different covariates. So, and we will interpret these parameters in the following ways. First, beta 0 is the intercept when both x1 and x2 are 0. And beta 1 indicates the change in the mean response per unit increase in x1 when x2 is held constant. And beta 2 can be interpreted vice versa. So the key thing here is the expectation. So the effect of the coefficients is effect on the expectation of the response when another covariate is held to be constant. For example, if we fix x2 equals to 2, and the expectation of y will be, in this case, if the coefficients beta 1 and beta 2 are both beta 1 equals to 2 and beta 2 equal to 5. So we can see that if we fix x2, the expectation of y will only be affected by x1. In other words, all one-dimensional expressions of the regression surface are lines. And we will also have regression models with greater than 2 predictors variables, and this will be in this format. So if we have p minus 1 predictor variables, then we can write the whole model as follows. So for each observation I, we will have p minus 1 different predictors, and beta p minus 1 will be beta k will be the coefficient for the case predictor. And we will also have a random error in the end. And for simplicity, we can rewrite the relationship in this way, where yi equals to beta 0 plus a sum k from 1 to p minus 1, beta k times xik, where beta k is the coefficient for the case predictor and xik is the observed predictor for the i's observation and case predictor. Here we include p minus 1 predictor because the first beta 0 is also one coefficient, and we can define the first prediction to be a constant equal to 1 so that we can simplify the whole formula in this format. Can let k from 0 to p minus 1. And we can use the similar least square function as the target function to be minimized, similar to the simple linear regression, and solve that function by taking derivatives and solve for the beta 0 to beta k. So I will introduce how the details of those target functions in tomorrow's lecture, and here I would like to introduce some more possible regression models. For example, the polynomial regression, which is a special case of the general regression model. So in a polynomial regression, the predictors, for the same predictor, we can add another predictor, which is, for example, if we already have xi, we can generate another extra predictor by using xi square as an extra predictor. In this case, the response function will become curvilinear, and we can also have other formats of the regression, which include for example, transform the response, which I have introduced. We can also introduce some interaction effects, and we find that if we believe that the interaction of the predictor, if we believe that the predictions are not independent, and we want to add some interaction terms for the regression. For example, in this regression, we have two predictors, and we also add the product of these two predictors as an extra predictor. And we can also add square terms. And the key thing is that all these, after adding all these extra predictors, the relationship between the response and the predictors are still linear. We can still use the linear expression to describe the relationship between yi and xi's. Finally, we can still do a t-test to test the coefficient for each of the coefficients, for each of the predictors. For the case predictor, its coefficient beta k, we can use the similar t-test to do the hypothesis testing to test whether beta k is close to 0. If we reject null, it means that the case predictor do have linear relationship with the response. And we can use similar decision rules to do for this hypothesis testing problem. And we can also use the LM function for implementation. Okay, I think here is practice, and I guess we do not have enough time for today's lecture, but you can make it your homework if you are interested, or we will also discuss this example problem on tomorrow's lecture. I will send all these slides to Eloy so that he can post these slides so that you can refer to the slide later. And yeah, that's all for today. And yeah, and if you have any questions or you have any suggestions on the topics or the way I introduce these things, you can send me an email. And if you are interested in doing all the practice problems, and you can also send your answer to me so that I can tell you whether you are doing things correctly. And okay, and last thing, I think that's all. And see you tomorrow.
Is it possible, I know this is, I guess, work for you to do, but is it possible for you to have Eloy send those slides tonight? Because there was just a lot of information and I was trying to keep up with writing everything, but I think it'll be easier to annotate the slides.
Yeah. Yeah, I will ask Eloy about this. So Eloy, are you still there?
Yeah, just it's gonna take some time to render the videos, and well, you'll have access to the slides by today.
Yeah,
Okay.
I will send you the slide immediately after this.
So yeah, I'm gonna send you a link to the Google Drive so you can drop off the slides there. Okay.
Oh, okay, that will also be great.
Sure thing.
Thank you.
Thank you, Eloy. Okay, I will stop here and stop the recording.